Welcome back to the deep dive. Today, we're doing something a little different, and I'll be honest, a little terrifying. We aren't just analyzing a topic from the safety of our desk. We're actually stepping into the pressure cooker. We are going to simulate a high-stakes technical interview for a senior backend developer role.
Yeah, and not just any developer role. This is,
Yeah.
well, the position we're looking at is inside a major financial institution, one of the big ones. And the project is a next-generation loans processing application.
Right. So the stakes they're incredibly high. We've got this whole stack of documents here that we're going to use to basically crack this interview. We have the official job description, which is just dense with requirements, things like Java, Spring Boot, microservices, and then blockchain protocols like Ethereum and Hyperledger Pursue.
And we've also got this really intense senior blockchain engineering drill-down cheat sheet and an internal guide on integration strategies. This isn't just about, knowing syntax. It's about knowing how to think like an architect in that environment.
Exactly. And that's really our mission for this deep dive. If you're listening to this, your goal isn't just to learn some blockchain trivia. Your goal is to prep yourself to demonstrate real judgment, solid risk management, and genuine architectural expertise. You need to be able to walk into that room or, jump on that Zoom call and prove you are the safest pair of hands for a multi-million-dollar system.
That is the absolute key word, safety. It really is.
Yeah.
When you're interviewing for, say, a startup, they want to know how fast you can build, how quickly can you ship features. But when you're interviewing for a bank, especially in a blockchain role, they want to know how well you manage risk. They need to know that you aren't going to be the person who accidentally loses all the collateral.
So here's how we're going to do this today. We're going to role play. I'm going to take on the role of the grilling interviewer. The U.S. tech lead who's seen it all. It's probably a little cynical and definitely does not suffer fools. And you.
I'll be playing the senior candidate. And my job is to deliver what we're calling the bank-safe answers. I'm going to try to model how you answer these questions, not just correctly, but strategically.
Okay, before we throw you into the fire, give us the core philosophy here. What's the mindset our listener needs to adopt, right now?
Okay. The mindset is this. You are being tested for judgment, not just for trivia. That's the most important thing. So when I, as the interviewer, ask you a question, don't just spit out a definition you memorize. Slow down. Speak in principles. And always, always, always tie your answer back to risk and governance. That is the single biggest difference between a coder and an architect.
I love that. Speak in principles. Okay, let's start by unpacking the job description. We need to know the terrain we're walking into. It mentions designing complex microservices architectures using Java Spring Boot, but it also very explicitly asks for experience with Ethereum, Hyperledger Pursue, and other EVM-based platforms.
Right, so this is a hybrid role. It's a bridge role, and that's where the real challenge lies. They aren't looking for a pure blockchain developer who only lives in Solidity. And they're definitely not looking for a generic Java developer who just, read a book about crypto. They need someone who can genuinely speak both languages fluently.
And the JD lists all these key responsibilities like modularity, testability, creating RESTful APIs. But it also highlights this need to ensure seamless integration and communication between front-end and back-end components.
That one line that's doing a lot of heavy lifting. Seamless integration in this world means managing the data flow between the front end, the back end microservices, and the distributed ledger. And that is not trivial at all. The blockchain is, by its nature, slow, it's asynchronous, and it's expensive. The bank's back end has to be the opposite. It needs to be fast, synchronous, and super reliable.
So how do we frame this for the interviewer? Let's say they ask us to summarize our approach to this hybrid world. What's the winning play?
There's one sentence from our source material that I think is the anchor for the entire interview. If you remember nothing else from this, remember this line. Blockchain defines what happened. Microservices define what we do about it.
Ooh, I like that. Let's say that again. Blockchain defines what happened. Microservices define what we do about it.
Exactly. This shows you get the separation of concerns. The blockchain is your source of truth. It's the immutable, auditable record. It proves a loan exists, it proves collateral was posted, period. But the microservices, that Java Spring Boot layer, that's your flexibility engine. That's where you handle all the messy business logic, the reporting, the user notifications, sending emails, all of that stuff.
This brings up a really interesting point about the difference between a junior and a senior candidate here. A junior candidate might come in and just start talking about syntax or, the specific version of Solidity they like to use.
Right. A junior developer talks about how to write the code. They get bogged down in the mechanics of it. A senior developer talks about state management, you talk about auditability, they ask the bigger questions like, how do we fix this if it breaks? Or, more importantly, how do we prove to the regulators that this transaction actually happened the way we said it did?
So right out of the gate, we are differentiating ourselves by just elevating the entire conversation. We're not just coding, we are architecting for audit trails and for governance.
Precisely. And in a loan processing application, which is the specific context here, that audit trail is absolutely everything. If the loan data on the blockchain doesn't perfectly match the data in the off-chain database, you have a massive, massive problem. A senior candidate anticipates that problem before they've even written a single line of code.
Okay, I think we have the right mindset. We know the terrain. Are you ready for the warm-up?
I'm ready. Let's do it.
All right, I'm putting on my grilling interviewer hat. Imagine we are 10 minutes into the interview, the small talk is over. I'm looking at your resume, and maybe I'm looking a little skeptical because, let's be honest, everyone puts blockchain expert on their LinkedIn these days. I want to see if you actually know your fundamentals or if you're just padding your CV with buzzwords. So I'm going to fire these at you rapid fire. I want like 20 to 40-second answers. Ready?
Okay.
Question 1. Don't give me the Wikipedia definition, and please don't tell me it's magic internet money. What is a blockchain, really?
A blockchain is a replicated, append-only state machine. Transactions trigger deterministic state transitions that are then validated by a consensus mechanism. The ledger stores both the transaction history and the resulting state.
Okay, stop right there. That was tight, very specific. Why those words? Why replicated append-only state machine?
Because I wanted to cut through all the fluff. By calling it a state machine, I'm signaling that I understand the fundamental computer science behind it. It's a system that moves from state A to state B based on a set of very strict rules. If you give it the same inputs, you will always get the same outputs. That's the deterministic part, and that's what a technical lead wants to hear, because that word implies reliability and predictability.
Got it. Okay, back to the grill. Question 2. You mentioned state. What exactly is state in the context of a smart contract?
State is the persistent key value data that's stored in the contract's storage variables. It's the data that survives across multiple transactions and defines the contract's current version of truth. It's basically the contract's memory that doesn't get wiped clean after a function finishes running.
Short and sweet. I like it. Next one. This is a classic trap for people who only have experience in Python or Java. Explain the holy trinity of EVM memory. Storage versus memory versus call data. Go.
Okay. Storage is persistent, and it's very expensive. It defines the on-chain state. You can think of it as being written to the hard drive of every single node. Memory is transient. It exists only during a function's execution and is wiped afterwards. It's like RAM. And call data is read-only input data, essentially the arguments that you send to a function.
And why does that distinction matter so much? I mean, why can't I just be lazy and put everything in storage?
Because of cost and safety, really. Storage is incredibly expensive because every node in the entire network has to store it forever. The S-store opcode is one of the most expensive operations you can perform in Ethereum. So the senior insight here, the thing you have to say is, only invariants belong in storage. Everything else, temporary variables, loop counters, intermediate calculations, all of that must be in memory or call data to save gas and to reduce what we call global state bloat.
And that's the senior add-on right there. Only invariants belong in storage. You're not just defining it, you're showing you care about efficiency and you respect the inherent limitations of the infrastructure.
And you're showing you understand the economics of it. If you put everything in storage, you will literally bankrupt the project with gas fees. And in a bank, efficiency directly equates to profitability.
Speaking of fees, question 4, what is gas? And don't just tell me it's a transaction fee.
Gas is a pricing mechanism for computation. It exists for 3 reasons. To prevent abuse, to incentivize validators, and to bound execution costs.
Bound execution costs. That's an interesting way to phrase it. Expand on that for a second. What does that mean for us, the listeners?
It's basically the EVM solution to the halting problem from computer science. You can't always predict if a given program will run forever or eventually stop. If you write an infinite loop in your code on a centralized server, you just crash your server. Annoying, but contained. On a blockchain, you'd crash the entire global network. Gas is what stops that from happening. Your code will eventually run out of gas, which forces a halt and reverts the transaction.
Okay, you passed the rapid fire round. You clearly know your fundamentals. You didn't just stumble through the definitions. Now let's move on to the mental visualization part. This is where the interview usually shifts from, does this person know the terms, to can they actually design a solution.
Right. This is the moment of truth. This is when the whiteboard comes out, literally or metaphorically.
Listeners, I want you to close your eyes for a second. Unless you're driving, please don't do that if you're driving. Visualize a whiteboard. You can smell the chemical markers. The air conditioning is humming. We're about to draw the architecture of a smart contract system.
Okay, I'm at the board. I've got the marker in my hand.
I want you to draw the box of truth. What does that look like on the board?
Okay, so I draw a single sealed box in the middle of the board. This box represents the smart contract. And the key thing is, once we deploy this to the blockchain, the code inside that box cannot change. It is completely immutable.
And that's the challenge, isn't it? Because all software has bugs. Or, business requirements change. How in the world do you fix a bug that's inside a sealed, unchangeable box?
Well, the short answer is you can't. You'd have to destroy the box, or rather you just stop using it and then build a brand new one. But that's really messy. You lose all the data, all the state that's inside. So on the whiteboard, I'm now going to draw a design pattern that solves this exact problem. It's called the proxy pattern.
Okay, walk us through the diagram. What are you drawing now?
Right. I draw two boxes side by side. The first box on the left I'm labeling proxy. The second box on the right is the implementation.
And which one holds the data? Which one holds the actual loan information, the money?
The proxy holds the state. That's the key. The data, the balances, the loan status, all that lives in the proxy contract. But it doesn't have the business logic. It's essentially a smart storage container with a forwarding address. It just points to the implementation contract.
So when a user or another service interacts with the system, which box are they talking to?
They're always talking to the proxy. And the proxy uses a special low-level EVM function called delegate call. It essentially says, hey, implementation contract, can I borrow your brain for a second? Mm-hmm. It runs the logic from the implementation contract, but, and this is the critical part, it executes that logic on the proxy's own state.
That is wild. So it's like it borrows the brain, but it uses its own body. The data stays put, but the instructions are coming from somewhere else.
That's a great way to put it. The brain is swappable. And here's the magic trick. If we find a bug in our implementation logic, let's say we calculated interest incorrectly, we just deploy a new implementation contract, a new brain. Then we just tell the proxy, hey, point to this new address instead. And just like that, we've upgraded the logic without ever having to move the data.
That sounds absolutely perfect. But hang on. We're in a bank interview. Is there a bank-safe twist to this? Because that, to me, sounds like it could be a massive security risk.
It absolutely is. And a sharp interviewer will probably ask that exact question. Why might a bank avoid using proxies?
That feels a little counterintuitive. I'd think banks would love the ability to fix bugs easily.
They love fixing bugs, but they absolutely hate hidden complexity. And proxies hide the code. When you look at the proxy's address on a block explorer, you don't see the logic, you just see a pointer to another address. It dramatically increases the attack surface. If someone could hack the upgrade mechanism, they can just swap out the brain for a malicious one that sends all the money to their own account.
So what's the senior stance here? Do we use them or do we not use them?
The senior stance is nuanced. You say, in high-value banking applications, sometimes you don't upgrade state, you migrate it. Which means you build a whole new system and you carefully move the users and their data over. But if you do use proxies, you treat an upgrade like a massive, critical database schema change. It has to be tightly governed.
Governed how? What does that mean in practice?
It means you don't just push an update. The upgrade function on the proxy must be controlled by a multi-sig wallet. It should require signatures from, say, the tech lead, the head of security, and maybe even an external auditor. And you add a time lock.
A time lock?
Yes. This is crucial. Even if all the required people sign the upgrade transaction, the contract itself enforces a delay, say, 48 hours before the switch actually happens. This gives everyone in the organization and even the public time to audit the new code. If it's malicious, there's time to cancel the upgrade.
And that ties right back to our core theme of risk and governance. You're saying that immutability actually improves auditability. If the code can just change under your feet in an instant, is it really an immutable record anymore?
Exactly. That is the kind of nuance that gets you the job. You show you understand the tool, the proxy, but you also deeply understand its dangers.
Okay, let's stay at the whiteboard. I want to test your security knowledge now. We're building a function to withdraw funds. Draw me a re-entrancy attack.
All right. I'm drawing two vertical lines on the board. One represents service A, which is the attacker's contract, and the other is service B, our bank contract.
Okay, set the scene. What happens?
Service A calls a function in our bank contract, service B. Let's say it's the withdraw funds function. Our contract checks their balance, sees it's okay, and then sends them the money. But here's the attack. Before our bank contract finishes its execution, the attacker's contract has a special piece of code that catches the incoming money and immediately calls back into our contract.
It re-enters the function before the first call even done.
Yes, it calls withdraw funds a second time. And because our contract, service B, hasn't finished the first run, it hasn't updated the attacker's balance in its state yet. So it still thinks service A has all its money. So it checks the balance again, sees it's okay, and sends the funds again and again in a loop until the entire bank contract is drained of funds.
That is genuinely terrifying. It's like tricking an ATM to giving you cash, but you manage to pull your card out before it deducts from your account balance, so you can just put the card right back in.
That's a perfect analogy. It's exactly that principle.
So how do we fix it? What do you write on the whiteboard to prove to me that you know how to stop this cold?
I write 3 words. Checks affects interactions.
Explain that pattern.
It's the golden rule of secure smart contract development. First, you check all your conditions. Does the user have enough balance? Is the contract unpaused? Second, you apply the effects. You update your internal state. So you set the user's balance to 0 internally. Third, and only then, do you perform the interaction. You make the external call to send the money.
So you update your internal ledger before the money actually leaves the building?
Exactly. By updating the state before you make that external call, you completely shut down the re-entrancy loop. If they try to call back in, the second check will see their balance is already 0. The transaction fails.
Simple, but absolutely critical. Okay, you've survived the whiteboard session. You can sit down now.
Thank you.
But don't get too comfortable. We are moving into the deep dive section now. The job description specifically mentioned Apache Kafka and microservices. This is the real-world stuff. This is where we bridge the slow blockchain to the fast bank.
Yeah, this is usually where the interview is won or lost. A lot of pure blockchain developers, they just don't understand enterprise integration. They kind of live in the crypto bubble.
So here's the problem statement. We have this loans processing application. The business team needs a report right now. They want to see all loans originated in the last 24 hours with a value over $10,000 grouped by the customer's region. Why can't I just query the blockchain directly for that information?
You can't query the blockchain like you would a SQL database.
Right.
It isn't built for that kind of operation. It's a linked list of blocks. It doesn't have indexes for region or value or anything like that. To answer that one question, you would have to scan every single block since the contract was deployed, parse every transaction, and filter it all yourself. It would take hours, maybe days. It's way too slow and astronomically expensive in terms of node resources.
So what's the solution? The outline calls this the shock absorber strategy. What is that?
Right. So we introduce Apache Kafka as the system's shock absorber. The blockchain gives us finality. It's the slow, hard, immutable truth. But the enterprise needs speed and complex querying capabilities. Kafka sits right in the middle and bridges that gap.
Okay, walk me through the entire flow. I'm the grilling interviewer again. How do you consume blockchain data in our microservices?
Okay. So first, the smart contract emits events. These are essentially cheap, structured logs on the blockchain. When a new loan is created, it emits a loan-created event with all the key data. We then have an off-chain service, which we call an indexer. The indexer's only job is to listen for these specific events on the chain. When it hears one, it grabs the data, normalizes it, cleans it up, maybe converts hex values to decimals, and then it publishes that clean data into a Kafka topic.
Wait, hold on. Why Kafka? Why not just have the indexer write it straight to a PostgreSQL database? Seems simpler.
2 words, durability and replayability. This is the key insight. What happens if your downstream database crashes and loses data? Or what if you find a bug in your reporting logic and you need to recalculate the last month of data from scratch? If you wrote it directly to the database, you're stuck. You've lost that raw feed of truths from the chain.
But with Kafka,
The events are stored in a persistent, ordered log. It's like a tape recording. You can just rewind the tape. You can have a new service spin up, read the event stream from the very beginning, and completely rebuild your database state from scratch. It completely decouples the source of truth, which is the chain, from the application's view of that truth, which is the database.
that's a massive advantage. It makes the whole system so much more resilient to, say, bad code updates in the microservices layer.
Exactly. You can literally destroy your reporting database and rebuild it perfectly at any time.
Okay, but there's a nasty technical edge case here that sounds scary. chain reorganization, or reorgs. What happens when the blockchain literally changes its mind about the past?
This is the absolute nightmare scenario for any integration pipeline. Sometimes, two miners might find a new block at roughly the same time. The network forks temporarily. Your indexer might be on one fork and see that block 100 contains transaction A, but then the rest of the network decides, actually, that other fork is the longer valid chain, and your block 100 gets discarded. It becomes an orphan block. Suddenly, transaction A never happened.
But wait, our indexer already saw transaction A and sent it to Kafka. Our downstream microservice has already processed it. Our database now thinks a loan was dispersed.
Exactly. We have a phantom transaction in our system. We have potentially dispersed a loan that does not exist on the official ledger. This is a five-alarm fire.
How do you prevent that? How do you fix it?
There are two main approaches. The simplest and safest is to wait for finality depth. You basically tell your indexer, don't treat an event as final, and send it to Kafka until, say, 12 new blocks have been mined on top of it.
Okay.
By that point, the chance of a reorg that deep is effectively zero.
But that adds latency, doesn't it? If a block is 12 seconds, 12 blocks is a couple of minutes.
It does. It might add 2 to 3 minutes of delay. But you have to ask the business question. In a loan origination system, does the user really need instant sub-second confirmation? Probably not. They're applying for a loan, not playing a video game.
And what's the second way? The more complex one.
If you absolutely cannot wait, then you have to design your entire downstream system to handle correction events.
Yeah.
If the indexer sees a reorg, it has to send a special message to Kafka saying, hey, that loan created event with ID 123, ignore it, it was a lie. But that is incredibly hard to engineer correctly. You have to handle undoing database transactions, rolling back workflows. It's a huge mess.
And the bank-safe answer is almost certainly to wait for finality.
Without a doubt. In a high-value loan system, you wait. You do not disperse a $1 million loan until you are absolutely 100% sure the collateral is locked on-chain. Speed is always secondary to correctness in finance.
And there's that summary insight again. On-chain events are the source of truth. Off-chain pipelines consume, enrich, and persist them for the application to use.
Correct. The microservices get to be fast and flexible because they are acting on a clean, validated stream of data that originates from the slow, steady truth of the chain.
All right, we are heading into the final stretch, section 5, the final boss questions. These are behavioral and strategic. The interviewer stops looking at the code on the whiteboard and starts looking at you.
Yes. This is where they test your philosophy. They want to know if you will fit the culture of a highly regulated institution.
Okay, first question. You seem to know a lot about Kafka and databases, so why not just store everything on chain? Why do we need all this other complicated infrastructure? Isn't the whole point of blockchain to be the one database?
This is a trap. 100% a trap. They are checking to see if you are a blockchain maximalist. Someone who thinks blockchain is a hammer and every problem is a nail. If you say, yes, let's put it all on chain, you fail the interview on the spot.
So what's the correct senior level answer?
The answer is, because it's prohibitively expensive, it's dangerously inflexible, and it massively increases the system's attack surface. On-chain code should only be used to enforce invariants.
Invariants? What do you mean by that?
Invariants are rules that must never, ever be broken. For example, you cannot withdraw more collateral than you deposited. That's a perfect invariant. That belongs on-chain. But the workflow, the business process, the email notification logic, the credit score calculation, all of that belongs off-chain where it's cheap, fast, and easy to change.
So you're basically arguing that the on-chain logic should be as minimal as humanly possible.
Minimal surface area means minimal bugs. If you try to put your entire business logic on the blockchain, you are creating an unupgradable monster that costs $50 every time someone clicks a button.
Okay, next final boss question. What, in your opinion, makes a smart contract production ready?
It's not about having more features. A production-ready contract has 4 key qualities: a minimal attack surface area, crystal clear access control, deterministic behavior, and this is the most important, one governed change management.
Governed change management, there's that theme again.
It means we know exactly who can upgrade the contract and how they can do it. Is it a single developer with a private key on their laptop? That is not production ready. That is a massive liability waiting to happen. It needs to be a multi-signature wallet held by leaders from different departments. It needs transparency and time locks.
Okay, now let's imagine the interviewer gets a bit aggressive. They lean in and say, look, ideally, we want to disrupt the industry. We want to be agile. It sounds like you're actively avoiding blockchain. It sounds like you're just trying to build a regular Web2 app with a few extra expensive steps.
Ah, yes. The defensive maneuver.
Yeah.
You have to stand your ground here. You cannot let them bully you into agreeing with bad architecture just to seem disruptive.
So what do you say?
I'd look them in the eye and say respectfully, I'm advocating for using blockchain where it adds unique and defensible value, which is for creating shared truth, immutability, and auditability, not where it just adds cost and complexity.
Ugh.
I'd follow up with, I'm not avoiding blockchain. I'm protecting the bank's assets by using the right tool for the right job. We use blockchain for the settlement layer, and we use microservices for the application and experience layer.
And that ties everything perfectly back into the specific client context, this next-gen loans processing application.
Exactly. Loans require strict, unimpeachable audit trails. That's the blockchain part. But they also require complex interest calculations, customer service workflows, and regulatory reporting. That's the Java and microservices part. The architecture must reflect that natural split.
We have covered a massive amount of ground here. I mean, we've gone from the raw definition of a state machine to drawing proxy patterns on a whiteboard to architecting a Kafka pipeline that can handle chain reorgs.
It really is a comprehensive toolkit. If you can speak to these points with confidence, you are already in the top 1% of candidates for a role like this.
Let's review the key takeaways one last time before we let our listener go. What's in the interview survival kit?
Okay. First, technical precision. You have to know the difference between storage, memory, and call data. And you have to know why storage is expensive. It's about the cost to every node.
Check.
Second, architectural patterns. The proxy pattern lets you upgrade, but it introduces governance risk. You have to know the trade-offs. And you must know checks-effects interactions to prevent re-entrancy.
Check.
Third, integration strategy. Kafka is your best friend. It is the shock absorber between the immutable, slow chain and your flexible, fast microservices. It solves the speed mismatch and gives you replayability.
Got it. Check.
And finally, the overarching philosophy, risk and governance. If you get stuck during the interview, if you get a question you just don't know the answer to, take a breath and pivot back to risk. Say something like, well, I'm not sure about that specific library, but the primary risk I see in that area is X, so I would design a control to mitigate that by doing Y. You will never, ever lose points for prioritizing safety in a bank interview.
Safety over speed.
Always.
Okay, now, before we sign off, I want to leave our listeners with one final provocative thought. We spent all this time talking about how to store data, how to move data, and how to audit data. But there is one huge thing we didn't touch on at all.
What's that?
Identity. In a decentralized loan system, how does the bank actually know who you are without putting your personal sensitive data on a public ledger?
Oh, that is the privacy paradox. You can't just write John Smith, Social Security number 123 onto an immutable public blockchain. That's a GDPR and compliance nightmare. You can never, ever delete it.
So how do you solve it? Zero knowledge proofs, off-chain pointers to a secure vault.
That is a whole other deep dive, a huge one. But it's something you should be thinking about. And hey, if you really want to impress the interviewer, you should ask them that question at the end. I'm curious, how is the team currently thinking about handling PII and privacy on a public ledger? Are you exploring any zero-knowledge identity solutions? Watch them sweat a little bit when you ask that.
I love that. Turn the tables, show them you're already thinking about the problems they probably haven't even solved yet.
Exactly.
All right, listeners, you have the cheat sheet, you have the strategy, you know what a deterministic state machine is.
You're ready.
Go get that job. Thanks for listening to The Deep Dive.
See you next time.